I did.
Yeah, thanks. Grab one of each. Grab one of each of the file on the front things. Okay, everybody got 2 minutes. Grab one of those 3 up there.
Yeah, so that's yours. Yeah.
All right, everybody. Let's get going today. So first off, just you probably already had this in. Good Lord, you got enough colors there? Okay, good. See the box of multicolored stuff up front. All right. So just a quick word here before. Did I get this recording? Yep, got it recording. Quick word before we get going. On the mask situation, the university has given the faculty, as you probably are aware, I don't know if you've seen the notices flying around, but given the faculty the prerogative to choose in class whether they mandate masks or not. I've decided that to not impose that in this class. That's just, again, that's my choice. Why don't you just grab one of each of those on the front there. I totally respect those who want to continue wearing masks. I will, of course, keep my distance, despite just having handed out everything, but I'll keep my distance. I hope that's with it. See some space. All right. So this morning is going to be a reasonably slowish walk through these thermodiagrams, right? How to plot them, that's the easy part. But there's an enormous amount of information that you can glean from these simple diagrams And the idea here is to walk you through an example before I send you off with your actual take-home exercise. So the actual take-home exercise is the single sheet here, right? The thermodiagram. That is what you will do in your own time. It's really an opportunity, as I said at the outset, a couple of things. One is an opportunity to really sort of build up your grade, butter up your grade, give you a chance to take your time at home on an exercise. And there's really no reason why you all shouldn't do superbly well on this. This exercise is not here to try and catch you out or make it impossible in any way, shape, or form. Right? That said, it's also not an exercise that can probably be done in 15 minutes. I am absolutely fine to make this due at the end of the semester. I don't think I have anything in the syllabus or anything online that has a due date. So that last lecture, whatever it is, Tuesday, the something of April, maybe early May. Our last get together is when I want to collect these. But being good meteorologists, we'll get this all done in the spring break. We'll be in the party, so that's good. But yeah, don't leave it till the end, if at all possible. So that's the context for today. And instead of just talking briefly about a thermodiagram, giving you the handout, telling you to go or to do it, I think it's just better if you go through this step by step, right? So we're going to use an example here. And so this handout here is the handout that we'll use today, right? I've built in a lot of explanation here. I know this is quite a thick little document, several pages long. I'm not going to read, I'm going to use this as a guideline to go through this morning for you. You're welcome to follow along. I'm not going to read it after verbatim. I don't like to do that in lecture, but I will point out some important parts here. And then the data that we're going to use this morning is actually in that handout as well. The third one, of course, is the thermodiagram itself. I've given you a color version on the front, a black and white version on the back. And then that's also uploaded onto D2L as well. So you can choose whether to do it in multicolored or to do it on the black and white. I always just prefer to do it on black and white because the colors then show up. But if you want to turn it into a global kaleidoscope, yes, please do. So do that. All right. Okay, so just as a reminder, these diagrams, there's a number of different forms. Sometimes, as I've said, I think I've mentioned, you'll hear the word skew T diagram. That's a very similar diagram, but it's just plotted in a slightly funky way. And I've used those before, and I find them a bit more confusing. These are called thermodynamic diagrams or thermodiagrams, and the particular type we're going to be using here is known as a STUV diagram, STUV. That would make a nice Wordle score. And they just plot more straightforwardly. And so if you went onto that website, as I've showed you, the Wyoming website, you can pull up different types of the one, but we're going to do a thermodynamic diagram that is the STUV diagram. And that's what the plot looks like. So as you look at this handout, then just to give you a quick sense of why we use these diagrams and the goals for this, the bottom line is that plotting a very simple data, right, which is just the temperature and the dew point vertically on these diagrams, allows you to then interrogate that vertical sounding to start talking about layer stability. You can start looking at not just which layers in the atmosphere are stable, you can start looking at parcel stability. So a parcel of air at any layer, would it be stable or unstable or conditionally stable? It allows you to begin to talk about severe thunderstorm potential, and meteorologists use this diagram. This is how they determine whether thunderstorms are likely to be severe or not, or at least whether the convection is going to be intense or not. And there's a lot of things that can come off these diagrams. Okay. So this is looking at stability and the potential for thunderstorm development, pretty much. All right. So I've just got some individual, I'm going to build up these individual slides, which ultimately all comes together to produce the color printout that you have. Okay. So there's a lot of background here. I go over what conditionally unstable is, stability, and so on. But let's look at these individually so that it's not as confusing as the final diagram. So the starting point for the tube diagram or the thermodiagram, left axis is always pressure. It's kilopascals here, right? But you can add a 0 and just pretend it's millibars. We use those interchangeably in meteorology. You've been used to millibars in this course. But kilopascals on the left, right? So millibars there. And temperature on the bottom, degrees Celsius. Okay, we use degrees Celsius internationally. So even the Americans have to acquiesce and go to degrees Celsius. They just plot so much more simply, right? Metric system. Come on, people. So it's temperature in degrees Celsius on the bottom. So these are isobars. The yellow lines I've got here are the isobars, right? The lines connecting places, locations of equal pressure. And the vertical ones are isotherms, the lines of equal temperature. Okay. And the green lines here are the dry adiabats, okay, again in degrees Celsius. So in 10-degree increments, that's 40, 30, 20, 10. That's a 0 degrees Celsius dry adiabat. And you can see that those are these constant rate lines at 1 degree Celsius. 100. Okay. We've got pressure, temperature, and the dry adiabats. Right, all good. Then we put on top of those, in these nice horn frog purples, are the saturated or the moist adiabatic lapse rates. Okay. And you can see that these are obviously sloped. Now remember, the saturated rate is variable depending on how much moisture there is in the atmosphere, but we take these at about 0.6 degrees Celsius per 100 meters. In very, very dry air, okay, and very cold dry air, moist saturated adiabats mimic very closely the dry. They're very close to them. Right? Remember that a dry is 1 degree Celsius per 100 meters. The saturated are only just slightly less than that in very, very dry air. Yeah, question.
Yeah, sorry. So the dry adiabatic lapse rate is the green line,
Yep.
correct? And then the saturated
It's the dash.
yeah. It's
Yeah.
dashed.
And that's why when you look at it in black and white, it's just going to be, wait a minute, this looks like a spaghetti diagram, which is actually a whole different type of meteorologic diagram you will learn to love later on. So does that make sense? Is that clear? Okay, so dry and saturated. And you can see that as temperature goes up here, the saturated lines begin to slope less, right? And that's because as you increase temperature, just think about our saturation vapor pressure curve. As you're increasing temperature and you have more moisture in that atmosphere, that's going to suppress the dry rate, right? Remember, it's just said the release of latent heat. The release of latent heat begins to suppress that rate. So that's why the lines go up like that. And then we have these little things. So these are the light. Let's just turn the front ones here. So these very light blue dashed ones, okay, those are parallel, and those go up to the top axis. Okay, so those are the isohumes. Iso line of equal humes, humidity. Okay, so those are the humidity lines. They're also referred to as the mixing ratio. I don't know if you remember when we talked about water in the atmosphere, and I had that little diagram. We've got an atmosphere, and we can express humidity in different rates, right? We've got relative humidity, we've got absolute humidity, specific. So specific humidity was the one I said that we're not going to talk about initially, but we will come back to it, and here we are today. We're going to talk about specific humidity. Specific humidity is how many grams of water per gram, kilogram actually, of dry air. I remember I said you can take that moisture out of the atmosphere, weigh it, and then how many grams of dry air. So it's very specific, which is why we call it specific humidity. So the slanting dashed blue lines go through to the top. These are isohumes. It's also referred to as the mixing ratio. How mixed is the dry and the wet air? Okay, so you can see the mixing ratio here down in the very cold air, right? Because remember, yuck, I hate this, but cold air can hold less moisture, warm air can hold more moisture. So here they increase very slowly, 0.2 to 0.3, 0.4, 0.6, 0.8, and so on, right? So the air is very dry here. And then as you start getting down there towards the right of the diagram, they get spaced out more quickly, okay, because the humidity goes up. So 15 grams per kilogram, 20, 30, 40. So just try and remember that this is the actual physical amount of water in the atmosphere, how many grams per kilogram of air. Okay, and then the final thing we put on the thermodiagram are these, and these are the heights, okay? So the heights are the dashed lines, the light gray lines that sloping sort of north-northwest to south-southeast there. And that's an estimate or a generalization, but it's pretty darn close. Remember, your pressure changes with height, your temperature changes with height, but more or less, okay, we've got elevation here. So this is height in kilometers. So if we just take the 5 kilometer height line here, all right, and we follow this dash 5 kilometer height line, it comes in at about 45 kilopascals or about 450 millibars. And remember, when we were looking at the 500 millibar surface, we said that occurs generally at about, well, it varies, right? It occurs at about 5.5 kilometers. So if we actually go to 5.5 kilometers, we start getting into the sort of mid levels of the atmosphere. But those aren't exact, right? That's just an indication of where the height is relative to those. So that's a complete diagram. That's the whole thermodiagram of all the lines that you'll need to complete the exercise. All good. Any questions? Okay. Let's see. What have I left off here? Isohumes, good. Oh, one thing, you will have to interpolate between lines here. So let's just take a look at this isohume here. This is 15 grams per kilogram. That comes down here, right? 15 grams per kilogram. And if your air parcel plots in between that, so if it plots right in here, it's between 15 to 20, you just got to estimate it looks like it's about halfway, so that would be 17.5 grams per kilogram. So there is some interpolation there, but the error bars around those are pretty low. Okay. All right. Let's see what else. I think that's everything I needed to observe. Okay. At the bottom of, I didn't put page numbers on here. At the bottom of this page that has the diagram, let me just read that, because that's really quite important, right? Note, when using the isohume, the vertical lines here, in a thermodiagram, the following rules apply. For any point representing temperature, so if you've got temperature here, and you've got a data point, there's a temperature, there's your data point, okay? Actual air temperature, and you've got an isohume going through that data point, right? So for any point representing temperature, the isohume that goes through that point tells you the saturation mixing ratio. A saturation mixing ratio. That's the same as saying saturation vapor pressure, right? What is the saturation mixing ratio? In other words, here's an air parcel. Let's say, I'm not going to put it on the map yet because you're going to do that in just a second. But let's say there's a dot on this map and this temperature is 20 degrees Celsius. And wherever that is, right, let's say it's right here, there's 20 degrees Celsius. And this isohume that goes through there is 15. So that isohume is 15 grams per kilogram. Everybody with me? Okay, that's you just plotted the data point here at 20, right here at the surface, and the isohume that goes through that 15, right? That's the saturation mixing ratio. In other words, if the air parcel at the surface with that temperature of 20 degrees Celsius was totally fully saturated, it would have 15 grams per kilogram of moisture in that parcel. Does that make sense? It would be sitting on the line if it was saturated. Okay, so that's the first one. For any point representing the dew point, right? So let's say your air temperature is 20 degrees, and let's say your dew point is here, and your dew point is 10 degrees, and it's got a line, right? So here's your air temperature at 20, and your dew point is down here at 10. This line here that goes up to the top here is 8 grams per kilogram. So that's 8 grams per kilogram of moisture at the dew point, and it's 15 grams per kilogram going through the data point. What can you tell from those two? 8 grams per kilogram at the dew point, and 15 grams per kilogram at the temperature. What can you calculate from those two? 8 divided by 15 would give you what? The relative humidity. Yeah, give you the relative humidity, right? Because remember, the dew point is the temperature to which the air must be cooled for saturation to occur, right? So if you're going to cool this parcel of air from 20 degrees to 10 degrees, then it would be saturated, and its 8 grams per kilogram would represent its saturation mixing ratio. It would be 100% saturated. But if its dew point is 10 degrees and it's plotted over here, and its air temperature is 20 degrees, okay, there's another way you can saturate it, and that's just keep shoveling more moisture in, 9 grams, 10 grams, 11 grams, 12 grams, and so on. All right, so that's an important rule, and you folks know that because we've gone through this. But I thought I just pointed out. We've got dry adiabats and saturated adiabats in the order. Okay, so let's get going. Some of you will do this more quickly than others. I just want you to do this by hand in class here, and we can work through it. So when you look at the table, there's your data table, right? Here's the data table. This is the first point. And this is all you will be given, and you are given it in the handout for the take-home exercise. You're just given the pressure, the temperature, and the dew point. That's your atmospheric sounding. So Morgan releases the weather balloon, and the data comes back, and that's the data that comes back from the weather balloon. Okay, so go ahead and plot that on the diagram, and I would use dots for temperature and X's for dew point. Right, and you can use red dots for temperature and blue X's for dew point. You can just use one color if you want. Fortuitously, there's a whole bunch of colored pencils here if anybody needs to use them, or you can just use a regular pencil, whatever the case may be. So you just start plotting your temperature and your dew point. That should be fairly quick. And then once you've done that, just join those data points up with straight lines. And I'll give you 5 minutes or so to get that done. So there's the first, I'm doing on the black and white there. So your first data point will be here. Right? There's your first data point, should be there, and I'll read that as the starting point.
Wait, where's the first data point?
Say again? That's your first data point. Pressure is 100 kilopascals, temperature is 40. See that? That's where your first data point should be. So just plot your temperature first and then plot your dew point. This is going to get very, very colorful and messy. Good. You know, if anyone's stuck on that first data point.
I'm on my mom's phone. Okay.
That's why that makes fun. Are you comfortable walking down here?
Oh, yes.
Oh, crap. No, sorry, don't plot. That's your exercise. That's your homework exercise.
What?
You've got a sheet. You use the data in the handout. I'm sorry.
Oh.
Yeah. Use the data in the handout. Or you could just get your whole homework finished here this morning, hand it in, and you walk out and be done. Dear Lord, I haven't had enough sleep. I think it's 4:30 this morning. Give me a break. Okay, I'm sorry. If you need another handout, so you're using the thermodiagram, and you're using the data on the screen and the data in the big thick document, and leave a single sheet of data to the side. That is to take from really. It's chaos at the outset. Okay, what's next? We celebrate.
And it's like, the first one we did was negative 30. Where does this come in?
So you'll read it. You come across and plot your temperature 25, and then you'll come to 80. Start at the bottom of that table, just work your way vertically upwards. Right? Makes sense? Does that help? Sort of?
Well, what about
You'll get there. So plot your temperature first and your dew point. Yeah, so then you plot your temperature, then you come back and you go back to 100. And then you'll need to do 25. Somebody wants to keep it 45 minutes.
Yeah,
Okay.
or I guess I'm going to buy.
Yeah.
It's like
Yeah.
20, it's from the accent, right?
Yeah, so that's a, so
So you go like 10 to 40. Yeah. Okay.
Yeah, so, yeah, there's some interpolation you've got to do between those, the vertical axis here. So this is, just count the hash marks, right? 90 to 100, these are hash marks. So these are every 2 kilopascals. And then they start getting into a better resolution, getting to 1 kilopascal. So you'll see that as you go up. At the end of this morning, you will be able to tell me what is the potential for severe thunderstorms on this diagram. But we're a little ways away. There you go, this is looking good. So your second data point should be there. Oh, another red one. I don't use this 6. Yeah, good. And then once you've done all your plots, just join the lines, straight lines. So do a temperature profile, viewpoint profile. Good. At some point, you should have that, right? Something that looks like that. Yeah. All those lines, you've got a temperature sounding. And then you'll have X's for the viewpoint, and your first viewpoint should be right there. And you'll do that. So you got a full sounding yet? Plus. And you've got the viewpoint. Yeah. Yeah. Make the line for the viewpoint and with the why not? Why not? Your vertical sounding, something like that. Okay. So yeah, we're taking some big jumps here. Obviously, the radio song would send you back much more data. not just at these mandatory levels, but to keep things simple, we'll do it at these mandatory levels. All good? Okay, you should have something that looks like that. Don't worry if you're not quite there yet. Keep going. Okay. So when you look at the handout there, and you'll see the table, right? And just remember, always, the dew point is always to the left of the temperature, right? It can be on the temperature, but it can never exceed the temperature in the atmosphere at this scale. When we talked about the saturation vapor pressure curve, you can have mixing of air, and you can get relative humidities above 100% for very short time periods, and then it has to go back to 100%, right? So we've got a temperature profile, and we've got a dew point profile, right? And remember, as temperature decreases with height in the atmosphere, you do get to a point where you start approaching the top of the troposphere. And generally, that temperature profile becomes what we call isothermal. In other words, there's no change in temperature with height, and the temperature just goes vertically upwards until you hit the stratosphere. So the isothermal layer there is at about 30 kilopascals, 300 millivolts, right? And the top of the tropopause would be probably somewhere up there at the 20 kilopascals. And if we kept going, you would probably find temperature would now start increasing again through the ceiling. Right. Okay. So so a couple of questions. One is, you can, I think it says that in your handout here. What is the actual mixing ratio? And what is the saturation mixing ratio? Let me just write those two up. So we've got R and RS. R is the actual mixing ratio, and S is the saturation mixing ratio, right? So R is the isohume that goes through the dew point. Okay. What's the actual amount of specific humidity at the surface? Just looking at the surface now. Okay. And what's the saturation mixing ratio value at the surface? Anybody want to shout out what they think that would look like? Actual mixing ratio and saturation mixing ratio at the surface. Basically, just take a look at what isohume goes through the dew point at the surface and what isohume goes through the temperature at the surface. If someone thinks they have it, just shout it out. What do we think the actual mixing ratio here is versus the saturation? Actual is? Shy. Yes. Maybe like 15.
Oh, 50.
Oh, 50. That's the saturation mixing ratio. Pretty darn close, right? Right at about 51-ish, somewhere in there is good. And I'll draw the lines in a second if you don't see that. And the actual mixing ratio is? What's the isohume that goes through the dew point at the surface? About, let's just say this is 51 grams per kilogram. And the actual mixing ratio would be about-ish, about 20, yeah, about 20, 21 grams per kilogram. And here they are, right? So all you're doing here is you're looking for the isohumes that go through the dew point. So here's your 25 degrees Celsius at the surface, and you draw a line straight up where you just follow that line. It mimics this one. So that's 20. I would have accepted 20, 21, 21 and a half. But if you start getting to 22, you're just starting to get a bit too high. That's the actual amount of moisture in that air at the surface. It's the dew point. Everybody needs to see that, right? That's the actual mixing ratio. Okay? That's the dew point at the surface, right? The saturation mixing ratio is right here. Right? So you plotted it at 40 here, and you follow a line that goes up there, and the line there is, 50-ish, 51, 52, It's between 40 and 60, but it's closer to 60 than 40. So if you look at those two, right, at the dew point, and so I'm just animating here just on the right-hand side there in that white space here. At the dew point, the actual mixing ratio here is 21 grams per kilogram. And the saturation mixing ratio, I've got it up here, it's 52, but again, I would have accepted anything around 50, 49, 53, something like that. Okay, so the relative humidity of the air at the surface is right at about 40%. Okay, let me just correct that. I said it was 51, we've used 52 as calculation. Okay, now I know this is a slight shift in your thinking from vapor pressure to specific humidity, but we have to use specific humidity in dealing with the thermodiagrams. So who doesn't get there? Please don't be shy. Everybody happy with how we calculate relative humidity? Yeah, absolutely, right? So we plotted a parcel of air here, and we used to do this, right? We used to have a saturation vapor pressure curve. And here we've got a parcel of air at 40 degrees Celsius. And we used to say, well, that's got a vapor pressure of X. And to cool it to its dew point, all right, at 25 degrees Celsius, it's now got to become totally saturated. At 40 degrees, to be saturated, it would have to be up there. So that's how we used to look at it. Here we're just looking at it in terms of how many grams per kilogram of dry air, right? And so here we are at 40 degrees. Okay, that's the air temperature at the surface. 25 degrees is the dew point. Obviously, that air is pretty dry because there's a divergence there. The isohue, the specific humidity line that goes through here, you just follow up. It's not lying on it. That's 40 and that's 60 that goes up to the top there. Okay, so you're trying to sort of interpolate somewhere in the middle. So that's 50, 51, 52 that goes up here, and through the dew point, that iso line there is right at about 20 to 21. So when you're thinking about humidity, moisture, you just follow those isohues to the top.
And then relative humidity is calculated by taking the. Wait, okay, I don't know.
No, keep going, walk through it. You're there, you know you're there.
It's taking the saturated vapor or the mixing ratio and dividing it by
The actual,
and dividing it
other way around. And so
actually
you-
divided by.
exactly.
So
So you-
R divided by R.
Exactly. R divided by Rx gives you the relative humidity. The actual amount of vapor there and the saturated amount of vapor. Okay, everybody good? Ooh, there's a bunch of information still to go. Okay, so that's it. So that's where we are. We've got a relative humidity of about 40%. All right. So now what we're going to do is let's lift. So the air at the surface is unsaturated, right? 40% is the relative humidity. Now we're going to lift. Whoops, too quick. We're going to lift a parcel of air here from the surface. So we're going to lift a parcel of air from the surface. Okay. So this is the environmental lapse rate that we're looking at here in red, and the dew point in blue. Now I'm going to tell you, go outside with a bubble of air right here and lift it. Okay. What do? You have, if you've got this, I think you're sort of 80% there, to be honest. You take that parcel of air, okay, you walk outside, it's hot, 110 degrees Fahrenheit, 40 degrees Celsius, dew point's 25 degrees Celsius. I'm going to ask you to lift that parcel of air into the surrounding ambient environment. Okay, what do you physically do on this diagram? Let's start with the more straightforward one. What are you going to do with that red line? That red dot? Take your parcel of air, you're going to do what? You move it along the dry adiabatic lateral. Okay? Don't do it yet, but conceptually that's the key. Okay? You're going to lift that parcel of air along the dry adiabatic lateral. Now we haven't talked yet about what dew point does when you lift a parcel of air, right? So you want to lift that parcel of air along the dry adiabatic lateral, and it's absolutely correct. You have to because the air is unsaturated. If this dew point was sitting over here, then you'd have to lift it at the saturated adiabatic lateral. But because it's back over here, that's very dry air, right? So you lift it at the dry adiabatic lateral. So you've got two blobs here. Here's a little green blob. I'm just going to draw your attention to them. There's the dew point. There's the temperature. And I'm going to take the temperature line here, and I'm going to lift that along this line, right? Along the dry adiabatic lapse rate. Not to that specific height, don't worry about where that ends up, just I'm lifting that air now up through the atmosphere. Make sense? And it's cooling at the dry adiabatic lapse rate. What do I do with the dew point? What on earth do I do with the dew point? So here I am at the dew point. Whoops, what do I do with it? As that parcel of air goes up, what does the moisture inside that parcel of air do? Now think in terms of specific humidity. We've got 21 grams per kilogram of moisture in that parcel. Is it liquid water or is it water vapor? It's water vapor. Why?
It's not at the lifting station.
Exactly. Ooh, not at the lifting condensation level. It's not saturated. Right. So you've got this parcel of air. Right now, you've just gone out there and you've just captured this parcel of air in this bubble. Okay, its relative humidity is 40.4%. Now we're starting to lift it. It's going to rise and it's going to expand and cool at the dry adiabatic lapse rate. Okay. Does the moisture change in that parcel of air? In other words, it starts at the ground at 21 grams per kilogram. And what happens to the amount of moisture in that air as you lift it? Does it change? Morgan, you're shaking your head left to right. Does it change or not? The amount of, exactly, it doesn't change. Why? It's just there, right? You've got 21 grams of water vapor sitting in that parcel. Right? It doesn't matter if I lift it, unless, of course, that water vapor is going to start escapating out the side of the bubble, right? But let's say it stays in that bubble, you're going to keep 21 grams per kilogram in that air bubble as it begins to lift. That makes sense, right?
Is the 21 grams per kilogram, that's like from what we just got.
Exactly. That's at the surface. Yeah, so that's the 21. This is the actual mixing ratio. That's the actual amount of moisture, i.e. in this phase, water vapor at the surface. So you just take this parcel and you're going to lift that along the isohue, the 21 grams per kilogram, right? Now that looks weird. You're like, well, wait a minute, we didn't do that with saturation vapor pressure. No, we didn't. Okay? But now we are. So at the surface, your air parcel does this. It starts lifting, it rises, expands, it cools at the dry adiabatic lapse rate. It goes from 40 to 39, 38, 37, 36, 35. Okay. And all the while, as that bubble is rising and expanding, it still has 21 grams per kilogram of specific humidity in there. But what's happening to the relative humidity as that parcel is going up? The relative humidity increasing or decreasing? It's increasing. Why? Because your air parcel is cooling towards its dew point. Okay? So you lift the parcels. So the dry one goes along that dry adiabatic lapse rate. And you lift the isohue at the dew point here, and you just follow the isohue. Okay? And where those two intersect, so here's the dry, here's the moist. There's the dry follows that line. This is following the isohue. It's following the isohue. And we get to this green line here. Okay? And I'm going to put a green dot on here. No, I like animation. So that line there, and there's the dry, there's the wet. That point right there is where the temperature in the parcel meets the isohue, meets the dew point. Everybody see that? So the temperature has gone from 40 to 39 to 38 to 37, right? The dew point is changing. It does change, but the amount of moisture in that parcel stays the same. You're keeping 21 grams per kilogram in there. And so you get to a level, and that level is the lifting condensation level. Right? That's the LCL. The lifting condensation. At that point, on the SVP curve, your parcel is now on the SVP curve. Guys, we've just gone straight left on that SVP curve. We're cooling it to the saturation vapor pressure curve. Right? That's what we've done in effect on the sounding diagram. So what height is the lifting condensation level? In other words, where does the cloud base start in this example? At about 2 kilometers-ish, right? Good, at about 2 kilometers, right? So here, it's actually just below that. And you go off to the right here, that gives you the height, about the lifting condensation level, where the temperature equals the dew point. Everybody good? Okay, awesome. We can calculate the lifting condensation level, and so there's the LCL. I've just scribbled up here a nifty little equation. This is an FYI, and I'm totally happy in the take-home exercise if you want to just eyeball it. Okay, if you want to calculate your lifting condensation level by eye. But if you want to be a super duper meteorologist, you can use a very simple equation here, right? You can calculate the lifting condensation level by taking A, which is a constant, and multiplying it by the temperature minus the dew point. That'll give you a more accurate and more precise level of the lifting condensation level. And that A is a constant. It's 0.125 kilometers per degree Celsius. Okay, so 0.125. If that confuses you, don't worry about it. Just take it as is. It's constant. So in other words, to calculate the more precise level here of the lifting condensation level, that lifting condensation level ends up being at 1.875 kilometers. How did I get 1.875 kilometers for the lifting condensation level? Well, I just took the dew point minus the temperature. 40 degrees minus 25 gives you 50 multiplied by the 0.125 gives you the 1.875. Then you take the surface dew point and the surface temperature in the parcel, and you just plug it into the simple equation, and it'll say to you, well, at about 1.8, 1.92-ish, somewhere there, that's where the lifting condensation is. You don't have to worry about that. Again, I'm happy if you do that by eye, right? So at the lifting condensation level, okay, we can do a few things. I shouldn't have this page. So at the top of the page here where it says to do, now we can calculate the value of LCL another way, right? There's the little equation. Okay, so and the pressure at the lifting condensation level, right? So the lifting condensation level is 1.865. If you come across to the left here, the pressure there is about 82 millibars. I mean kilopascal, right? 820 millibars. That's the pressure at the lifting condensation. Okay. So now we're at the lifting condensation level, and there's a couple of questions there, right? We can calculate the dew point, the mixing ratio, the saturation ratio, mixing ratio, and the relative humidity, and so on. Okay. Okay. So I want to just read this out because this is important, right? Once a rising parcel of air has reached the lifting condensation level. Now we're not at the point where we are determining whether this is rising or not. Once it's reached the lifting condensation level, any further rise causes what? Any further rise causes some of the water vapor to condense out. Right? So at this point here, the relative humidity is 100%, and any further rise causes that moisture to start changing phase from water vapor into liquid water. Okay, and any further rising would follow the saturated adiabatic lapse rate. Right. So if you were physically drawing this in, and you'll do this in your take-home exercise, you'll raise that along the dry rate, you'll follow the isohume to the lifting condensation level, and then you will lift it, mimicking the closest saturated adiabatic lapse rate. Right, that makes sense. So what's happening dynamically inside that air parcel from a moisture perspective, okay, at the lifting condensation level? Well, if you're at the lifting condensation level here, okay, what is the mixing ratio? Well, the mixing ratio is still 21 grams per kilogram. Remember, there's no water going out or coming in your bubble, right? The amount of moisture in there is still 21 grams per kilogram at the dew point. But now R equals RS, right? The mixing ratio, your actual mixing ratio is now your saturation mixing ratio. your relative humidity is 100%. Does that make sense? Okay, so R equals RS. All right, cool. Okay, so here's what I just wanted to emphasize. Although water vapor is condensing into liquid droplets above the lifting condensation level, one assumption that can be made, and this is really important, right? One assumption that can be made is that as that air continues to lift, and as it continues to cool now at the saturated adiabatic lapse rate, right? So although the water vapor is condensing into liquid droplets, one assumption that can be made is that all of the liquid water, as well as the remaining vapor, are carried upward with the parcel, right? So as it continues to rise and cool at the saturated rate, all of that moisture goes with both the vapor and the liquid water. Because remember how big are water droplets, right? Well, they're tiny, okay? A rain drop, a cloud droplet is 10 microns, and any kind of vertical uplift is going to bring it all up. So as that air is continuing to rise and cool at the saturated rate, yeah, it's shedding water vapor in terms of excess liquid water. It's condensing out, but it's all getting carried along, okay? They're all carried along. This is an assumption, a good assumption for cloud droplets, which are so small and light that they're easily carried along. What this means, okay, is that the total water mixing ratio, the total, right, the total amount of moisture in that parcel, the total water mixing ratio is conserved, right? We're not losing moisture, we're not gaining moisture, but total water mixing ratio is the sum of the water vapor and the liquid mixing ratio, right? So now we've got this RS is the actual amount of water vapor in the parcel, and then we've got RL. You'll see how this plays out in a second. RL is the amount of liquid. Okay? Everything's cool and groovy when it's unsaturated, when the relative humidity is below 100%. Okay? Because then you're dealing with the actual vapor, and it's rising, it gets to the dew point. Now it's at the dew point. Okay? It's at the lifting condensation level, and that's got 21 grams per kilogram of moisture in it. Okay? As that parcel keeps rising, it still has 21 grams per kilogram of moisture in it, but some of that becomes liquid water, and some of it becomes or stays as water vapor, if that makes sense. All right, cool, cool, cool. Okay, so here we go. So at the lifting condensation level, what is the dew point at the lifting condensation level? Right, so here you're at the lifting condensation level. The dew point, you can just go straight down. That's 22 degrees Celsius. Right, so the dew point does change. Now, I never mentioned this before in any of the previous lectures because it always confuses. The saturation vapor pressure curve, we just said we cool it to the SVP and you drop it down. But as air parcels go up, the dew point does change a little bit, right? So we get here to the lifting condensation level, and you just come down, and that's 22 degrees Celsius. The actual amount of moisture at the lifting condensation level is still 21 grams per kilogram. It doesn't change, right? That's the physical amount of moisture in that parcel. Is that a realistic assumption? Well, I mean, moisture is, of course, moving in and out, right? But in the big scheme of things, we have to isolate these parcels to try and determine the stability. Okay? So, any questions there? Everybody good there? So all you're simply doing is you're taking a temperature and a dew point, a dry air parcel, and in the exercise I've given you a dry air parcel. You lift it, it follows the dry rate. The dew point follows the isohum until they meet at the lifting condensation. That's where the relative humidity is 100%, right? That will make sense, right? At that point, you continue to lift the air parcel and you follow the saturated rate, okay? So here we go. Now we're at the lifting condensation level. Where's your air parcel going to go? It's going to follow, and I'll explain that in a second. It's going to follow the saturated adiabatic rate. You want to see that? Here's the dot. And now it's lifting and it's following the nearest saturated rate, which is that one there. So there it goes. I've sort of tried to mimic. Okay. And let's get it up there to 40 kilopascals, 400 milliwatts. Does that make sense? So go ahead on your diagram and just plot that data point. Just plot 40 kilopascals somewhere between these two saturated adiabatic lapse rates here, but, you know, sort of closer to the one on the right-hand side. So just kind of in light pencil, or just imagine following that curve up and then stopping at 40 and putting that dot there. Let's get to that point. That makes sense. Making good time. We're going to use every minute of today. Okay. Anybody struggling to put that dot on? I know you're interpolating between two saturated levels. Looks good. Perfect. All good. Bueno. Okay. So we're at the lifting condensation level, and you haven't decided whether the atmosphere is stable or not. We're just saying this is what you have to do. So then that follows the saturated adiabatic lapse rate, and we said let's stop at 40 kilopascals, right? So what on earth is this? That's this X here. Well, if we go back to the lifting condensation level, as that air parcel follows the saturated adiabatic lapse rate, and it's cooling at the saturated adiabatic lapse rate, how much moisture stays in that parcel? If it's 21 grams per kilogram at the lifting condensation level, it hasn't changed from the surface. It hasn't changed to the lifting condensation level. You think it's going to change above the lifting condensation level? Nope. So 21 grams per kilogram, right? That makes sense? Again, unless you're cheating and you're shoveling vapor in or sucking vapor out, but we're assuming that that's not the case. So as that air parcel lifts all the way through the atmosphere, it conserves, it keeps this specific amount of humidity in. It keeps 21 grams per kilogram. At the surface, it could have held 52. So that's why it was only relatively saturated at 40.4%. It follows up here to the lifting condensation level. It keeps its 21 grams per kilogram. And as the air continues to rise and cool at the saturated rate, it just keeps that 21 grams per kilogram. No matter where you are vertically, that air will have 21 grams per kilogram of moisture in it. That makes sense? Okay, that makes sense, guys. Almost there, right? So here we are at 40 kilopascals. This air parcel here has cooled to the saturated rate over here. Now we've got this little horizontal line. So first off, someone tell me how much water vapor is there in that air parcel at 40 kilopascals, right? What's the vapor mixing ratio, or the amount of water vapor in there? How much water vapor is in that parcel at 40 kilopascals? Who's got a number for it? That's the total amount of moisture. How much water vapor is it? You think? Ooh, interesting question. What do I do? Right at that parcel. It's what? Bingo. It's 8, right? Because here you are, okay? Your air has risen up here and it's cooled and it's cooled, and I said, let's stop here, and it stops right there. And then you look up at the isohue here, and it's 8 grams per kilogram, okay? That's the total amount of water vapor, 8 grams per kilogram. Is the air saturated? It's above the lifting condensation level. Is the air saturated? Absolutely, it's saturated. So that 8 grams per kilogram is the saturation mixing ratio. It's the actual amount of water vapor, and it's the saturation, it's sitting on the saturation vapor pressure curve. Does that make sense? So this horizontal distance here, and this may bamboozle, so don't panic. That horizontal distance is the amount of liquid water, right? We've got 8 grams per kilogram. You just told me is the saturated vapor pressure, SVP, the actual amount of water vapor. But I've just told you that we're not losing or gaining water, so we had 21. Well, where did the difference between 21 and 8 go? That's the amount of cloud. That's the condensation, the liquid water level, the liquid mixing ratio.
So is there a specific reason why you stopped at 40 ppm?
That was just a Disney.
So you could technically stop anywhere.
Absolutely, good question. No, this has nothing to do with stability. Yeah.
Is your answer still gonna be the same no matter where you stop, or?
Well, it'll be, right, it'll be different. You can get up here, let's say we stopped at 30, that's a great question. We stopped at 30 and it would be right here. The actual vapor pressure would be 4, that's the saturation vapor pressure. This X would still be at 21, right? So 21 minus 4, I'm not a great mathematician, but that would be 17 grams of liquid water that's condensed out. Does that make sense? So all we're doing here is we're diverging from the saturated vapor pressure or the saturation mixing ratio and the amount of water that is in that faucet, right? So on the SVP curve, I was saying, well, that's kind of squeezed out. That's what's happening. Water's getting up. Okay, everybody good? All right, cool. Now, does that air parcel lift all the way through along the saturated adiabatic lapse rate? Well, no, it can't, right? Because it goes here and you start lifting it, and what happens? It's not going to go through there, right? Because the air parcel cools at the dry adiabatic lapse rate and it reaches the ambient temperature, and therefore it does what? It stops, okay? So now what we do is we take, you can do this in light pencil. Now we've got to determine whether all of these shenanigans are going to work. Okay, we've got to determine, is the atmosphere stable, and is this air parcel going to go from 40 to 25 meters the LCL, keep going up along the saturated adiabatic lapse rate? It may or may not. So go to each point and just draw a very light line, okay, at each point that mimics the dry adiabatic lapse rate. It can be a very, very tiny little error, okay, at each point that mimics the dry adiabatic lapse rate. So you're probably thinking, well, why are you doing that? Okay, because here what we want to do is we want to determine what we call layer stability, okay? Which layers there are stable in that atmosphere? Layer stability. Okay. So what we're doing here is we're saying, here's this air parcel, okay? And it is, so there's a little confusing because that's the actual temperature line. So this air parcel here goes up there. Well, we know that this is going to keep rising, right? Here, this air parcel is cooling at the dry adiabatic lapse rate. And here's the actual temperature. So from 40 degrees at the surface, is that air going to rise? Absolutely, it's going to rise. It's going to rise because it's warmer than the surrounding environment, right? The environmental lapse rate lies to the left of it. Does everybody see that? So from the surface up to where this air parcel meets the ambient temperature, is that air stable or unstable? From 40 to that point. Stable or unstable? Absolutely, unstable, right? Because as this air begins to rise, anywhere along that line, its temperature is warmer than the surrounding air, okay? And here, if the air started at this point and cooled at the dry adiabatic lapse rate, would that be stable or unstable? From there, relative to the environmental lapse rate. Stable or unstable at this point. There's your line mimicking the dry rate. There's the actual environment. Got to be stable, right? It's much colder than the ambient air. Here, there it's going at the dry rate. It's got to be stable because it's colder than the ambient air. Here, it's almost lying on top of it. You couldn't really determine. That's going to be a neutral atmosphere. Right here, it cools at the dry rate. It's stable, much colder than the ambient environment. Right? All you're doing is you're just taking each data point and just drawing a line mimicking the dry adiabatic lapse rate and saying, if that was the situation, would that layer be stable or unstable? Okay. So I'm going to draw this in on the right-hand side and speed this up a little bit. And I'm going to draw these layers in here. So these are the layers that are stable and unstable. Right? This lower layer from the surface right up to here, where that air parcel meets the ambient environment, that's unstable. The lower layer here is unstable. Okay, so that's good. But now we've got this, it's not an inversion, but we've got this isothermal layer. That's where the instability ends. So there's a big U, that's unstable. All of this is stable because all of these arrows are now lying to the left of the actual environmental lapse rate. We determine this one as being neutral because that lies on top of the line, and the rest is all stable. And on the right-hand side here, what I've done is I've just colored in hash marks here, these two, you just see them on the right there. Those are the layers that I've colored in as the isothermal ones, right? Just for frame of reference. So this little layer here. Does that make sense? So that's what you'll do in the take-home. You'll just take each data point and just draw a little light arrow and go, okay, is that layer going to suppress or is it going to enhance vertical motion? Okay, cool. What this is, and this is really important, right? This layer here, this vertical isothermal layer, so your second data point and your third data point, okay? I could have drawn that as an inversion, which is, you know, an inversion is the most stable layer you can have, right? But I've just drawn it as an isothermal layer here. So in other words, if you went outside and just kicked your air bubble and said, go for it, it would rise, it would cool at the dry adiabatic lapse rate. It would be unstable here because it's always warmer than the environment, but then it would stop right there. It wouldn't go through that layer, that isothermal inversion layer. So this is acting as a cap. And I've just labeled it there as the side. We've got a cap there, okay? And then not quite an inversion, but close to it. And the BLU, right, that doesn't stand for the Brown-Lupton. BLU, we call that the boundary layer, right? The boundary layer is any air layer from the surface up to a cap, an inversion, or any kind of lift, okay? So there's all sorts of overturning. You can get air moving around here, convection going there. You can get air to rise, but that air is not going to go any higher than about 90 kilopascals here, or at a height of about 750 meters. There's a lid there. There's a cap, right? A stable boundary layer. Okay. All right. So let's draw this little theoretical air parcel here. You can do this, right? So take your air parcel, draw a line from 40, follow the dry rate, okay, and then draw a line up following the dew point to the isotherm to the lifting condensation level. We just did this, and then there's the dashed line going up to the top of the atmosphere. So just do that quickly now, okay? Just do. I've already said it's not going to punch through that isothermal layer, but don't worry about it. Just draw in the lifting of the air parcel, the theoretical lifting of the air parcel from the surface up, and then the dew point mimicking the 21 grams per kilogram to the lifting condensation level. You can just do a little dot there, LCL. We've already done that, right? Okay, so there's the LCL. I'll label it there for you. And then just follow the dash line on the saturated adiabatic lapse rate, all the way up to the top. Someone asked earlier, is that going to go all the way to the top, or this is do it all the way to the top? That is the theoretical track of what your air parcel could potentially do under this situation. It's not going to do it. You'll see why in a second, but that's what it could do, right? So you just follow the dry adiabat to that lifting condensation level of 8.75, vertical one, and then why is that air parcel not going to go to the lifting condensation level and follow the green dashed line? That's what it could do, but why is it not going to do that? Because of the cap, right? No matter how unstable that lower layer is, this air will rise, and it will rise to that level, and it's only going to rise to that level. It should. I've got to get to the LCL. It's not going to get there. It's not going to eat its way through this layer here. And it certainly is not going to follow that dashed line until something happens, right? Okay. Does that make sense? You've just drawn in the theoretical asset. And that's what you see on these sounding diagrams. You'll see the solid line, temperature, you'll see the dew point, and then you'll see this theoretical ascent where it rises at the dry adiabatic lapse rate, changes to the saturated adiabatic lapse rate. Okay. This little Z, as you call them, or Z as I do, right? This Z subscript I, I've just labeled that, and that's a standard nomenclature. That's the height of the cap, right? That's the base of the cap. If you had pollution pouring out into that atmosphere and a smokestack was billowing pollution, that pollution would go very quickly vertically because it's unstable, and then it would spread out underneath that cap, right? So that's ZI.
So the base of the cap is where the person needs to be.
Correct. Good. Base of the cap, ZI, that's the base of the cap. A couple of other key things, right? Ooh, yummy. This is the most important point on the diagram, the LFC, right? The LFC is that point there where if the air parcel had gotten to its lifting condensation level, in other words, if it had been able to push through the cap, it hasn't, but if it could have, and if it had continued to follow that dashed line along the saturated adiabatic lapse rate, the LFC is the point where that air parcel along that saturated adiabatic lapse rate passes over the environmental lapse rate, right? Passes over the sound. Everybody see that? You go up a little bit, you go up a little bit, and it crosses over that sound. That's known as the level of free convection. Okay? Incredibly important, the LFC, the level of free convection. Right? So the level of free convection is exactly that. If you can get the air parcel to that data point, you can take your hands off it, and it'll continue to rise on its own, free.
Sorry, there's just so many lines. of-
I know, it's awesome.
So it's when the point where the black dashed line that we just drew across the red line.
Yeah. The level of free convection is right there. Okay, so it's where you've looked at the parcel of air, and it's met its lifting condensation level, and you're following the saturated adiabatic lapse rate, and it crosses over your original temperature profile.
Why does that not serve as a cap the same way that like the other one does?
It does serve as a cap, right? This is a cap. Okay, so I'm just saying, if you can get the parcel here, if you could get it 10 feet above there, why does it not serve as a cap? Because as it's rising and cooling along the saturated rate, its temperature is warmer than the surrounding environment. It's always warmer than the surrounding environment. Great question. Okay, yeah, I know there's a bazillion lines here. There's no way around it. It's just not.
I just want to make sure I understand it.
Yeah.
So the level of free convection is if the parcel passes the cap, like it would rise on its own.
Absolutely. Okay, we came back and we looked at layer stability and we said, well, this layer was unstable and this is stable, this is kind of neutral, this is kind of stable. Okay, that's all cool, not literally, but that's neat from a layer perspective. Now we're taking our little parcel and we're trying to determine, is my parcel stable or not? How is that going to go up, right? We know it's going to get to this point and no further, but if we could get it further, it would get to the lifting condensation level. If we could get it further, it would follow the saturated rate, and then we would have to do no more work, okay? Beyond the level of free convection, it would continue to rise on its own accord.
What is the red one?
Which red line?
So like
The solid one?
Yeah, the level of free convection is where the saturated adiabatic lapse rate crosses over the.
On this diagram, yeah, it may not be the saturated rate, it may be the dry rate, but in this instance, it's where, because your parcels have already reached its lifting condensation level. If it hadn't reached the lifting condensation level, right, if the dew point was down here and it was only meeting up here, as long as it's crossed over that ambient environmental lapse rate, yeah, it's the ambient, it's the ELR, your original red, the original red line is your environmental lapse. Oh, we're nearly there. Oh, we're nearly there. Okay. And so this is being recorded and I'm going to upload this as a video for everyone to see. Right. And then when we come back from spring break and you've got Cabo and Cozumel out of your system, then I'll do a quick recap because there's a bunch of lines here, right? We only had was like 8 data points to start. Question?
No.
Okay, no more questions. All right. This little orange shaded area here. Oh, there's more colors. Yeah, that's, listen, you've got the colors here, right? There's no crying in baseball. So it's orange. Yeah. So this little shaded area, it's going to get better in 5 minutes. This little shaded area is really, really important, right? This shaded area is the area between your environmental lapse rate and your dry and saturated curve along your theoretical potential. Maybe I could move along this path thing, right? So this is called SIM, convection inhibition. It's the area between the cap, right? It's the area between that, from that cap to the level of free convection, right? SIN, convective inhibition, right? It's the strength of the cap is what it is, If you've got no shaded area, you've got no cap and you're off to the races. If you've got a big, gigantic shaded area, that means you've got a lot of work to do to get this air parcel through the cap and beyond its level of free convection. So you just shade in that little area that follows the environmental lapse rate to the level of free convection and back to the level of condensation level, just that little diamond area. That's sin, right? Everybody, this is awesome. We celebrate confusion. Okay. All right, everybody with me? Oh, one thing I needed to point out, the very top here is the LOC, that's the limit of convection, right? So if you can get your air parcel through this cap and just above the environmental lapse rate, it's going to rise along that saturated rate all the way until it stops, until it becomes stable again, which is right at the top point there where your environmental lapse rate and your saturated rate meet. So that's the limit. There'll be no more uplift. Okay. So that's the situation right now with your sounding. Okay. You've got a lower level that's unstable, right? You've got a cap there because of this isothermal almost inversion. And your parcel is going to rise to this point and this point only, no further. Okay? Because of that cap. Z subscript I, the base of the cap. Right? This is the amount of convective inhibition, right? That's the strength of the cap. And we've got to get our parcel to the limit of free convection, right? So for a free Starbucks, how do we do that? How do we break the cap? We cry. How do we break the cap? I know you guys have this. You want them to. But how do we get that parcel of air to go through that cap? What can we do? How?
A mechanism.
What's your mechanism?
Latent heat.
Bring a cold front in. Or what's a nice way of breaking the cap without a cold front? Remember we talked about this with stability? Heating the ground. Heating the ground. What happens if we suddenly heated the ground and our temperature went from 40 to 45 degrees Celsius? Okay, now that's pretty warm, right? 40, that's 115 degrees Fahrenheit. It's not unrealistic. If we heated the ground to here, and the parcel started rising with the dry adiabatic lapse rate, and the dry adiabatic lapse rate, and the dry adiabatic lapse rate, and we followed the isohume here, the dry adiabatic lapse rate, that would meet above the ambient environmental lapse rate.
What do you use the ground?
You bring the sun out.
Like,
It's like, get the blowtorch, right? I mean, the sun comes up and it starts heating the ground. Yeah? Yeah. Okay. Or, as Justin said, you bring a cold front in. Okay. You bring a cold front in and the air goes, well, I've got nothing else I can do except go up. It's the only thing I can do. Put a cold front in there, whether it can be the most stable environment you want, that air's going to rise up. Or you put a mountain range there. Does that make sense? All right. Okay. Hang in there for 3 minutes because I want to introduce you to the final term. Yeah.
The green dash line, was
Which the green dash line?
Yeah.
So that is your air parcel once it had theoretically gotten to its lifting condensation level and theoretically continued to rise and cool at the saturated adiabatic lapse rate. Just mimicking the saturated adiabatic lapse rate. What, the green line?
Yeah.
This, so that's the sounding, right? That's the air parcel moving along the saturated adiabatic lapse rate. And now we're going to introduce you to CAPE for 2 minutes, 3 minutes. CAPE is, okay, so we get the air parcel through the boundary layer, we get it through the cap, we get it to the limit of the level of free convection. So how strong are the storms going to be? Like, we all want to know that, okay? Is it just going to be a gentle storm and a little bit of rain, or are we going to have to run for the hills? So we can use this thing called CAPE, which is the convective available potential energy, right? What is the convective available potential energy? And that is, oh, here's another color, awesome. That's the shaded area between Caitlin's saturated adiabatic lapse rate, the green dashed line, okay, and your environmental sounding. So, I thought you were going to get a blight with like 6 data points. Okay. So that shaded area is the convective available potential energy, right? It's the area, the distance, it's how big the area is between where your parcel is rising and cooling along the saturated adiabatic lapse rate and the ambient temperature of the environment. Now, if the ambient temperature in the environment did this, right? If your sounding did this, did that, let's say we had a little isothermal, and then it really cooled off quick, your convective available potential energy would be huge. That shaded area would be huge, right? Or if your sounding did this, and it went up there, and you got it to the limit of free convection, and then we had another inversion up there and a bit of that, you wouldn't have any convective available potential energy except that little sliver over there. Okay, so the size of the area, and physically, I want you to think in terms of that's the rate at which your parcel is cooling along the saturated rate to the rate at which your ambient environment is cooling, right? Remember, we can destabilize the atmosphere enormously by cooling. So we bring in cold air, and that destabilizes the whole atmosphere, and your parcel goes point and just flies up to the. Why do we want that? Because we want it to keep cooling rapidly as it rises. Does that make sense? I'm not going to show you because I need about 10 minutes. I'm not going to show you how to calculate that. We'll do that when we revisit the size of the area gives you the convective available potential. Well, that's a very nice diagram. Like it. Very confused. So what I recommend is you what? I'm very confused. Good. That's so. What we'll do is we'll come back after spring break, right? I'm going to spend a bit more time reviewing this. I want to explain it, and then my strong advice to you is do not leave this till the last minute, right? Because you can see all you got to do is put a few data points, and then I've got the dreaded discuss. I want you to tell me what on earth is going on in this environment that I give you. People will go into spring break. Right. I love it. Yeah, that's good.
I'll be like close to that.
Anybody going anywhere exotic?
No. Florida.
I'm going to the Belize.
Oh, very cool. Biosphere too. Florida.
Yeah.
Our son's been to Florida, isn't it?
Yeah. Or like that's not what I draw. Like it's like yeah, all that stuff.
Oh,
That's it. Next year, always.
Wow.
So you'll be announced. You won't see it as part of the initial study of work. It'll be kind of pull up pretty quickly. So you know, I've got a whole bunch of people in a folder, and we've got some very fun. It's an awesome trip.
Thank you.
Yeah. That was fun.
That's great.
For me. You too.
Thank you.
Mm-hmm.